So in this video, I'm going to try doing the practice questions on my little tablet device here because I have a pen, which is nice. Let's get started. This is photoelectric effect for grade 12 advanced physics. Which of the following best describes the photoelectric effect? So in the previous video I kind of mentioned it's like photons, electricity, photons, electricity. What is the best option here? This is going to be the reflection of light. No, it's not reflecting. The emission of electrons when the metal is heated, nothing to do with heat. Absorption of photons by atoms causing them to emit visible light. No, we're not getting them to emit visible light. It should be electrons that are coming out. The emission of photoelectrons when certain metals are exposed to electromagnetic radiation. This is basically light, shining light on it, and electrons will come out. So this is a good answer here. That's very nice. Okay, it provides evidence for which of the following? Well, it's not the wave nature, that was Young's double slit experiment, so it's not that one. Particle nature, that's the whole point, actually. The whole point of this is light being a particle. It's what won Einstein the Nobel Prize in this. The absorption of light by metals, it's not providing evidence for that. It's happening, but that's not what it's trying to find. The reflection of light is not part of this at all. We're trying to make electricity move with light shining on it. Particle nature of light, as I've explained in my previous video with the photons and the electrons. Which will decrease the energy of the photon? Well, if you remember, E equals hf, or you could say hc over lambda. I want to decrease the energy, so I should decrease my frequency, directly proportional, or I should increase my wavelength. That will be inversely proportional. So increasing the wavelength, yes, that's a good one. Decreasing means no. Increasing the frequency, no, because I want to decrease it. I need to decrease the frequency. So 1 and 4 are the two choices. So 1 and 4, which one's that? That is B. Very nice. Over here on the right hand side, let's move along. What do we have here? The energy of a photon is inversely, well, I've literally just said it in the previous question, inversely proportional to the wavelength, directly proportional to the speed. In the photoelectric effect, if it has a wavelength more than the threshold frequency, so the wavelength being more, it didn't say energy being more, wavelength being more. So the threshold, hc over lambda. If I have a higher wavelength, I have less energy. That could have been energy. I have less energy, I will not be able to eject. I need to have the minimum energy to eject. I need a minimum E equals hf. I need a minimum frequency to have the minimum energy. In this case, I don't. This is saying my wavelength is greater. If the wavelength is greater, nothing happens. So there will be current, no electrons will be ejected, no electrons will be emitted. Yes, because a big wavelength means small energy. So remember that from the previous video and from the formula, both ways. Which feature supports the quantum model of light? The emission depends on the amplitude of the light wave? No. We can make it brighter, increase intensity, nothing happens. Increasing exposure with time? Also no. We tried it in the simulation, we kept the light shining on it for a long time, nothing happened. It just didn't have enough energy. The emission depends on the frequency, not its intensity. Yes, that is true. It depends on the frequency or wavelength, but not the brightness. Brightness is the number of electrons that get ejected. So electrons can be ejected even if the light is below the threshold? No, they will not be ejected. It will not have enough energy to leave the atom. That's not good. So for question 7, it's asking about the role of the photocell. This is the thing that's making the electrons actually move. So we're trying to get electric current when the light shines on it. So it's not for storing electrical energy. We're not trying to amplify the signal. We're not doing any energy conversion. We want to generate an electric current when photons strike. This is a good one. We want to create electricity when light hits the surface. So D is a good option there. Which of the following will decrease if I was to decrease the brightness of the cell? So if I wanted to figure that out, if you remember, the brightness relates to the number of electrons coming out. So the brightness means less bright, less light photons coming in. Each photon coming in will be reduced. I will maybe cancel a photon if I decrease the brightness. That means the number of photons per second will also decrease. Frequency and wavelength and speed is not affected by the brightness. It's the same brightness, it's the same wavelength, same frequency, same light, but just more of it, more photons. All right, question 9. We have a light beam falling on a metal surface. Electrons are ejected. Which of the following is true if the intensity, which is the brightness, if that's increased, what happens? If it's brighter, more photons, more electrons. Number of photoelectrons, these two are good. Wrong. Maximum kinetic energy, well, like I said, it doesn't affect the energy. It's just more electrons coming out with the same energy. So if I have 3 bits of light coming in, I will eject 3 electrons. If I increase the brightness, I will have more light coming in. I will eject more electrons. Each one of these will have the same energy. It's just each one carries the same energy, and they come out with the same energy. Just more of them. So this is the best answer over here for question number 9. Okay, if a metal has a work function of 3 eV, which of the following can eject an electron? Well, you can see that we have eV and nanometers. There's a little shortcut that we can use to figure this one out. Well, first thing is this. If you notice, we can calculate the EV of each of these, and as long as it's higher than 3 EV, then it's fine. It will eject. Or we can do one calculation. All we need to do is see what the wavelength here will be. So if I can figure that one out now, I can go ahead and do the wavelength. The general formula, by the way, is the energy is supposed to be 1240 over the wavelength, which is in nanometers. This was the rule, the little shortcut that we can use. I can flip it around. I can do 1240 divided by E, so I'm just going to swap these two around, and that will end up becoming 3 EV. 413 nanometers. Now that I know this is the cutoff wavelength, my wavelength should be greater or less. Which one is it? Is it going to be this one, or is it going to be these two? If you forgot, remember the rule, E equals hc over lambda. They're inversely proportional, aren't they? So, in order for the electrons to come out, I must have a smaller wavelength than the threshold. I must have a greater frequency, but a smaller wavelength. So straight away, I can see that this one and this one are smaller, which means they will have more energy that I need. I need the equivalent of 413 nanometers. These two are good. This is higher wavelength, which means less energy. This is not good. So in this case, we can say this is the best answer, C. What is the energy in EV? Well, I've kind of just mentioned it there for you, right? You can use the little trick. We have nanometers and we have EV, no problem. So I can go ahead and solve that. I can do E equals this little 1240, and I'm going to divide that by 620. If you put that into your calculator, you will get 2 EV. By the way, this 1240 is basically it's a constant, right? Because we have hc over lambda. That's a constant, that's 6.63 times 10 to the minus 34. That's a constant, that's 3 times 10 to the 8. And that is wavelength, and if we keep it in nanometers, we can cancel some of the zeros. Long story short, multiplying them out together will always give you this number, if this stays in nanometers. This is going to make life a lot easier for us. Okay, two metal surfaces, A and B, and they are having work functions, very nice. If the same light shines on the surfaces, which one describes the difference between the electrons? More electrons are emitted from A than B. I probably shouldn't have skim read that. Let's read the whole thing again. Two metals, A and B, different work functions. The work function of A is greater than the work function of B. That's what I didn't really read. A needs more energy to leave. So if I have a light coming in, shining, let's say 100 joules, I'm making this up now, 100 joules of energy. This one needs maybe 80 joules to leave. If I shine it on another one, maybe I only need 50 joules to leave. Well, whatever energy I have left over will be just a little subtraction, right? Whatever energy here will be a subtraction, so all of that's 80. That becomes 20 joules of kinetic energy. 100 minus 50, that's 50 joules of kinetic energy. So which describes the differences between the energies. So you can see that this one has less energy, this one will have more energy remaining, because I didn't need as much to escape. This is related to energy, not the number of electrons. The number of electrons are not related, so these two are definitely going to be gone. The number of electrons is related to the brightness. It said somewhere that the brightness is the same. Same light shines. Very nice. Electrons from A have less energy than B. Yes, my made-up scenario, that was only 20. That was 50. This was A, this was B, by the way. That means C is good. It needed more energy to leave, meaning it had less leftover energy afterwards. If I'm trying to find the cutoff frequency, well, obviously the formula is this F naught. I'm asking for frequency, so that's just going to be that over, what is this? Over H. That's it. This is asking for frequency, so that means which one is the best answer over here? I can see that that over that is this one here, C. If I asked you for wavelength, you could have used this one over here, because that would have been hc over lambda, rearranging. Would that have been right? Let's find out. If I asked for wavelength, you have this equals hc over lambda, and if I wanted to do it, actually wavelength would have been hc over this one, not b. If I asked for wavelength, you would pick A. If I asked for frequency, you pick C. So just in case the exam they try to change it around a little, make sure you know both of them. Make sure you know this and this. Which of the following statement is incorrect? Threshold frequency does not depend on the metal used. Of course it does. This does depend on the metal used. The threshold frequency is different for different metals. The emission of photoelectrons is instantaneous. That is a correct statement. Photoelectric emission does not occur below the threshold frequency. That's true. It must have the minimum frequency to occur. The photoelectric current increases with the frequency. No, the current itself, which is the number of electrons, will not increase. So this is also wrong. There's two options in this question. I think there was an update which I don't have. But yeah, anyway, this is also incorrect. The photoelectric current increases with the brightness. This increases with the brightness or intensity. All right. Photons are incident upon a metal surface. You have a work function. You have the maximum kinetic energy. You need to figure out what the energy of the photon is. I showed you E photon is going to be my work function plus my kinetic energy. So all I need to do is we'll just add them, right? You have the work function of 8. You have the kinetic energy of 12. 8 plus 12 is clearly 20 eV. Very good. Next, moving on. A light of wavelength has this and this. Calculate the maximum kinetic energy. Well, that's here now. I'm looking for Ke. I can rearrange. Ke equals the energy of my photon, whatever it is, minus my work function. I don't know the energy of the photon. I can quickly solve that, of course. You can go ahead and do 1240. It's in nanometers and it's in EV. 1240 divided by 300, if you remember from before, that's what we did. And I can subtract I'll put that over here, that's my EV. I can subtract 3.90 from it. That is the work function right here. I'm subtracting that from here. Once you put that into your calculator, hopefully you'll get, I think it was 0.23 volts, electron volts. A would be the answer for this one. In this question here, we are seeing in terms of frequency. We're talking about in terms of frequency, what is actually happening, how much is going to be left over, kinetic energy. Same idea as the previous question. Ke is my energy of my photon, so that's my E photon, minus the work function. Okay, well, how much of the work function do I have? And in this case, there are no actual numbers. You can see the frequency. You can see this is the light. This is the photon energy. It's illuminated, so this is the photon. And this is the general threshold frequency, F naught. So this is 2.5 times bigger than F. So I have 2.5 times bigger minus, well, just on its own, 1, yeah? Of course, it's written in HF. As you know, this equals HF. So I'll write 2.5 HF minus HF. That's the equivalent of this is 1 lot of HF. This is 2.5 HF. 2.5 minus 1 leaves me with 1.5. That's all this is. So this is just saying 2.5 times bigger than this. This is 1. This is 2.5. Subtract them. 2.5 minus 1. Okay, now we have another question. Photocell, very nice. It has this aluminium work function. What is the stopping potential? Same idea here. So now it's asking for the stopping potential. What did I say to you before? Do you remember the stopping potential ends up being the same as the kinetic energy? The stopping potential was the work W equals QV. That's what we started with. The energy is the EV. This is the energy. And that happens to be whatever energy was left over. Remember, it ejected, and once it ejected, the leftover was kinetic energy. So, if I wanted to figure this out, the stopping potential would be the same as the KE. I will take my photon, and I will subtract my work function from it. So this is same. Stopping potential is the same as the KE. Very good. What am I doing? Yes, 6.4 minus 4.08. Stick that into your calculator, you will get 2.32. Very nice. Next, moving on to the next question over here, down to question 19. What is the cutoff frequency? Here's a little graph. So one thing you need to know, this is the stopping potential. This is frequency over here. There are two types of graphs. One of them is this, and one of them is simply the energy graph. The energy graph will look something like this, and it'll be kind of the same idea. That's my frequency. And if you were to go back, over here, this happens to be my work function, and this general graph, that's the kind of things you need to know. This is the not stopping potential, this is the cutoff frequency. Anything below that, nothing happens. Anything above that, I have more energy, more and more. So this will kind of end up becoming the kinetic energy. This is stopping potential. It's related to the same way. Remember, E equals EV, and this is going to be E divided by E equals V, but not important right now. We'll get to that later. What's this? This is nothing happening until we reach 5. When I reach 5, I start to see the photoelectric effect taking place. So the answer directly will simply be D, which is 5. Okay, very nice. Now, moving on over here. What is the work function? So the work function, if this one over here, we can go ahead and figure it out. E equals HF, right? Remember the formula? HF. I have H, 6.63 times 10 to the minus 34, and I'm going to multiply that by the frequency, which was 5 times 10 to the 14. 5 times 10 to the 14. Solving that into your calculator, you should hopefully get this number over here, 3.3 times 10 to the minus 19. Next, you need to find Planck's constant from the data provided in the graph. Generally speaking, in a previous graph here, well, obviously E equals HF, right? So H will be E divided by F. That would be fine, E divided by F. But that's obviously not fine, because this is good for kinetic energy, but down here, this is not kinetic energy. This is stopping potential. So instead of doing that then, instead of writing E, I will write EV. I will do H equals EV over F. That's it. All I need to do is figure out my V and my F, and I can go ahead and solve it. So we can find the slope. Find the slope taking 2 points. Once you've figured out the slope, I'll take this point and maybe this point over here. I can go ahead and find the slope. So my voltage was 2. I'm going to multiply that by E because EV. So I'm going to have to do 2 times 1.6 times 10 to the minus 19. And I'm going to divide that by my frequency, which I have is 10 minus 5. Remember, rise over run. Rise over run. Kind of assuming you know that. y2 minus y1, x2 minus x1. That's rise over run. My y2 minus y1 was just simply 2 minus 0. F is here, x2 and x1, 10 minus 5. So it'll be 10 times 10 to the 14 minus 5 times 10 to the 14. I'm just writing the whole thing out. Put that in a bracket, why not? Solving that, you will directly get your answer for equals HF, not HF, you'll get the value for H, which in this case ends up being something like this. 6.4 times 10 to the minus 34. You can go ahead and check that. And I'm done with the practice questions on the multiple choice. Thank you.